A 2,000 metric ton reactor vessel suspended hundreds of feet in the air relies on steel braided lines no thicker than a human wrist. It defies logic that a material used for rigid skyscrapers can be spun into a flexible thread and tasked with holding such immense industrial weight. While everything has a breaking point, these cables handle loads that should theoretically snap solid steel. Today, we're breaking down the hidden engineering of wire rope, from its molecular secrets to the absolute limit of this technology, the Taisun crane's world record lift. How does a single cable hold when a solid bar would snap? The answer lies in a design that allows the rope to breathe under pressure. To understand why a crane cable is so resilient, the starting point is the raw material, high-carbon steel. Steel's strength is rooted in its molecular lattice, which resists being pulled apart under immense tension. To visualize this power, consider a solid 1-inch diameter bar of high-strength structural steel. While this bar can withstand approximately 50 metric tons of tension before failing, its solid state is a fatal flaw in a dynamic lifting environment. A solid bar is too brittle to handle the shock loading, vibration, and wind resistance common on a heavy industrial construction site. Bending a solid bar around a winch drum creates massive internal stress, leading to microscopic fractures that migrate through the object at the speed of sound, resulting in a catastrophic failure with zero warning. The manufacturing of wire rope is a precision-engineered process designed to eliminate these solid-state weaknesses. It begins with high-quality steel wire rod, which undergoes a process known as cold drawing. The rod is pulled through a series of progressively smaller tungsten carbide or diamond dies. This cold work process does more than just reduce the diameter. It physically elongates the steel grains and aligns the molecular structure, which significantly increases the tensile strength and hardness of the metal beyond its original cast state. Once drawn to the exact specification, these individual wires are fed into a high-speed planetary stranding machine. This machine rotates the wires around a center wire to form a strand. For example, a common construction might involve 19 or 25 wires twisted in a specific lay to ensure the strand remains tight and uniform. In the final stage, known as closing, multiple finished strands are helically laid around a central core. This core, often an independent wire rope core, IWRC, consisting of a smaller internal wire rope, provides the vital radial support needed to prevent the outer strands from crushing each other when the rope is under a 1,000 metric ton load. This multi-layered construction ensures that if a single wire has a microscopic flaw, the crack is physically blocked from migrating to neighboring wires, keeping the entire load path secure. Beyond the raw numbers, has the industry's historical reliance on solid structures actually been a hidden weakness in modern engineering? If you were to cut a modern crane cable used on a machine like the Liebherr LR1800, you wouldn't see a uniform mass of metal. Instead, you would see a complex, multi-layered living machine. A high-performance wire rope consists of 3 primary components: the core, the strands, and the individual wires. At the center sits the core. In heavy-duty applications, this is usually an independent wire rope core, or IWRC. This core acts as the foundation, providing support to the outer strands so they maintain their shape even under crushing pressures. Wrapped around this core are the strands, typically 6 to 8 of them, which are themselves composed of dozens of individual high-carbon steel wires twisted together in a specific lay. The mystery of the wire rope is that these parts are not fused together. They are designed to move. As a crane hooks onto a 500 metric ton load, the cable actually breathes. The individual wires slide against one another by fractions of a millimeter. This movement allows the rope to distribute the tension equally across thousands of individual steel filaments. If one wire is slightly shorter or under more stress, it can shift its load to its neighbors. This internal friction is managed by specialized lubricants infused into the core during manufacturing. As the rope bends over a sheave, the lubricant is squeezed out to the surface of the wires, reducing heat and wear. This creates a paradox. The cable is at its strongest when it is allowed to move. Consider the specifications of a typical 64mm wire rope used in offshore construction. It may have a breaking strength often exceeding 300 metric tons. By weaving these wires in a lang lay or regular lay pattern, engineers ensure that the torque generated by the tension in the wires is cancelled out by the counter-rotation of the strands. This prevents the cable from spinning wildly when the load leaves the ground. It is a symphony of balanced forces. Even the strongest cable ever forged has a rated capacity. If you have a rope rated for 40 metric tons and you need to lift 400 metric tons, crane engineers use the parts of line. This is the primary function of the hook block, that massive, multi-ton assembly of pulleys or sheaves that hangs from the end of the crane's boom. When a crane operator reeves the cable through the hook block and back up to the boom tip, they are essentially creating a mechanical advantage system. For every additional loop of cable or part that goes between the boom and the hook, the load on the actual winch is halved. On a massive Manitowoc MLC 650, the operator might use 16 parts of line. In this configuration, if the hook is lifting a 400 metric ton load, each individual segment of the wire rope is only feeling 25 metric tons of tension. This is how a single cable is able to lift the weight of a small fleet of locomotives at once. However, this comes at a cost: speed and length. Because of the laws of physics, if you want to lift a load using 10 parts of line, the winch has to pull in 10 feet of cable to raise the load just 1 foot. On a deep-sea construction vessel, this might require a winch drum holding 5,000 meters of steel cable just to reach the ocean floor. The precision required in this process is staggering. The sheaves in the hook block must be machined to a tolerance of less than a millimeter to ensure the cable doesn't rub or chafe against the sides of the groove. If the cable is slightly mismatched to the sheave size, the lateral pressure will flatten the rope's circular profile, causing the internal wires to pinch and break. As we multiply force through simple geometry, does it make you wonder if the most complex problems in your industry could be solved by returning to basic physical laws? To see the absolute pinnacle of what wire rope can achieve, we must look at the Yantai Raffles shipyard in China. Here stands Taisun, the most powerful gantry crane in existence. Taisun was designed for a singular purpose: to lift entire integrated decks onto oil rigs in one single movement. In its record-breaking lift on April 18, 2008, Taisun hoisted a barge loaded with water ballast weighing 20,133 metric tons. This was not a lift performed by a single winch or a single hook. Taisun utilizes a series of massive hoisting units, up to 20 synchronized winches controlled by a central computer system. The scale of the rigging is difficult to comprehend. The crane utilized over 50 kilometers, roughly 31 miles, of high-strength wire rope. Each of the multiple hoisting points had to be perfectly tensioned. If one winch pulled even a few centimeters faster than the others, the resulting shock load could have snapped the lines in a chain reaction of steel. The cables used on Taisun are engineered with a specific fill factor, where the gaps between the circular wires are filled with plastic or smaller diameter wires to maximize the amount of steel per square millimeter. At this global scale, the wire rope is no longer just a tool. It is a critical piece of infrastructure. Despite the 20,000 metric tons pulling downward, the cables held because the system was designed with a redundancy that a solid material can never replicate. A steel beam can look perfectly fine until the very microsecond it snaps in half. Wire rope, by contrast, is a communicative material. Because it is made of hundreds of individual wires, it is designed to fail gracefully. In the industry, we operate at a safety factor, typically around 5 to 1. This means if a cable is rated to lift 10 metric tons, it actually takes around 50 metric tons of force to break it. This massive buffer accounts for wear, tear, and shock loading. The braid provides visual warnings. Before a crane cable snaps, the individual wires on the outer strands will begin to break one by one, known as crowning. An inspector can look at a cable and see these broken fish hooks. If they see more than a specified number of broken wires in a given length, the cable is retired. Other warning signs include bird caging, where a sudden release of tension causes the outer strands to bulge outward, or kinking and diameter reduction. Because the load is distributed across so many filaments, the failure of 10 or even 20 wires doesn't result in the load falling. It simply reduces the safety factor, giving the crew time to set the load down. A solid bar has no such mechanism. Once the first molecular bond breaks in a solid rod, the rest follows instantly. In a wire rope, the discontinuity of the strands acts as a fire break for cracks. A fracture in one wire cannot jump to the next because there is a physical gap and a layer of lubricant between them. This is why the wire rope remains the undisputed king of the heavy lift. If the very equipment we use is designed to signal its own failure before it happens, are we as industry professionals listening closely enough to the warnings in our own projects? The wire rope is not a set-and-forget component. In the heavy machinery world, environmental conditions, salt spray, extreme heat, and abrasive dust are constant enemies. On a massive crawler crane like the Liebherr LR13000, the tension on the main hoist is monitored in real time by load cells accurate to within 1%. These sensors communicate with the crane's onboard computer, which will lock out the controls if it senses an approach to the crane's rated limits and unsafe operating conditions, preventing the system from ever getting near the actual elastic limit of the steel. The chemistry of the steel itself is also a variable. By adding manganese and chromium, manufacturers can adjust the rope's resistance to abrasion or its ability to withstand low-temperature environments, such as Arctic construction sites. A rope designed for a harbor crane in Singapore is fundamentally different from one destined for an oil sands project in Canada. Furthermore, the winding on the drum must be perfect. If the rope is allowed to overlap unevenly, a condition known as stacking, the weight of the outer layers can crush the inner layers, destroying the core's ability to support the strands. On high-capacity winches, Liebus grooving is used on the drum to ensure the rope follows a precise path layer after layer. This level of detail is what separates a standard construction site from a high-stakes engineering feat. We are managing a complex metallurgical system that must perform flawlessly every time the hook leaves the ground. Thanks for watching Hard Hat Industries, your source for serious machines doing real work. If you like this, hit like, subscribe, and turn on notifications so you don't miss what's next. Until then, keep your head down and your gear running.